Hello everyone, we are Group MOJITO. My name is Wenhao Wang and I'm your presenter today. Today we're here to give you a brief presentation about our group members, the methods we use to solve the problem set, and also some examples of our final results. There are 3 members in our group. All of them are currently pursuing the PhD degree in computer engineering with Northeastern University. Our research interests mainly include hardware security, computer architecture, hyperdimensional computing, machine learning, and cloud FPGA virtualization. We use both software and hardware to help us to solve the problems. For software, we mainly use 2 tools this time. The first one is IDA, which is shown in the left side of the slide. It helps us by disassembling the code pieces into function tree, which help us understand the main function of the program better. The second one is a Ghidra, which is shown at the right side of the slide. It helps us to reverse the ELF file. It first disassembles the ELF file into the assembly, and then decompile them into C-like pseudocodes, which make us have a better understanding of the detailed function and how this program works. Now, we will give you an example about how we solve the problem sequence by using the tool Ghidra. When we load the sequence.elf in the code browser in Ghidra, it will first disassemble the binary file to many series of assembly codes. We can see what happens for each register and memory address by checking the assembly code easily. Further, Code Browser provides the decompiler which tries to transfer the assembly code into C-like pseudocodes. Nonetheless, we have to admit that the transferring is not always perfect. Sometimes we need to double-check in the assembly code window to make up some flaws in the compiled window. For the sequence.elf file this time, all the C codes for the reverse engineering are fine. Therefore, we don't need to do anything for the assembly code again. The diagram shown in this slide is the structure we inferred from the decompiler. The main challenge is in the challenge function. The kernel function for the decryption is the Fibonacci function, which generates an organized sequence. Then, there is a judge statement. If the first input word is equal to the sequence 24, while the second input word is equal to sequence 28, we will get the information correct as the output of the board. Otherwise, C5 board will tell us incorrect. After that, what we need to do is just to read out the value of the sequence 24 and also the value of sequence 28. After that, just input them in. We think the problem should be solved. After the works mentioned in previous slides, we demonstrate the result here. In this video, we can see that when the Wi-Fi is connected, the greeting line is shown up soon. Then, we input what we inferred previously, 0 and 38. After that, the C5 board will return the correct message to us. For hardware, we mainly use 2 tools to help us. The first one is analog discovery of digit. As shown in the right side of this slide, we connect the Hi-Fi board with analog discovery to find out the functionality of each output port. The purpose for this is to find a proper port which can control the whole board or even read out some sensitive information out from the RAM on board during the execution. The second one is the bus pair rate, which is shown in the left side of the slides. The bus pair rate is often used in the reverse engineering of many IoT systems of RISC-V system on chips. We connect the 10-pin JTAG port to bus pair rate with it and try to activate the debug mode on board. That's all for today. Thank you very much. Have a good day.